want to afford to have something is that, so I'll do my, the easiest way to understand this is to do these, the simple beam axle. This suspension does not go up and down, all it does is roll. Here we have a car, and it has a pivot between the axle and the car at variable spots. So the car has a center of gravity, let's say, right here. If you put your pivot between the car and the axle at the CG, when you go around the corner, that car does not roll. The car stays flat. How many buy that? Let's see if we're following. Not really. Maybe that wasn't good of a picture. Let me do a different one. Have a look. Let's do it in two colors. Okay. So let's do this car. Here's the car. This axle just goes straight through. It's not a real suspension. All it does is roll. And I put a pin between those two right there. Let me say that the center of gravity of this car is also right there. Then when I go around a corner, the acceleration force on the center of gravity is applied to the center of gravity. If that is directly in line with this pivot pin, then there's no tendency to cause the car to roll. So that's the beauty of a high roll center, is it doesn't roll a lot. So now the trick is to do the compromise, to say, get the roll center high enough that we minimize the amount of roll, but not so high that we have jacking, or that we have a lot of jacking. And so for streetcars, somewhere in the 5-inch range, roll center height, maybe 3-inch to 7-inch, something like that. That tends to work well. Okay. So let's see. So this is all review, but important stuff. Now, how much does it roll? So that's a function of what's called the roll stiffness. So let me change this picture. Let me put the center of gravity of the car up higher. And it has a pivot now, let's say right there. So now we do have what's called a roll moment based on this little distance. I'll call it h. So there's an MA force to the outside applied to the CG, and we have a roll moment equal to MAH. Now there's going to be springs between this car and the suspension. So I'll make a little spring here and here. And those springs are going to resist the roll. So you can imagine that as the car rolls, one will be compressed, this will be extended. And so both are helping you resist the roll. Even though, and this is again where the static weight of the car can be a little confusing. So a 3,000-pound car means that these springs are very compressed. When you go into roll, one gets longer, one gets shorter. But let's see. In reality, they are both in compression because they still have the car weight on them. But for the purposes of understanding how they are rolling, you cancel out that initial car weight, and you just look at this spring getting longer, which means that it's like tension, and this spring getting shorter in its compression. Okay, so there's a lot of equations for processing these spring rates to determine how many degrees your car will roll.
So we basically just can neglect the weight of the car?
The initial weight of the car will determine how far those springs compress, but once they are compressed, if you want to find the net effect of a corner, then you just consider that additional force and you cancel the initial weight.
So, for example,
if you have a car and say you built a system that when it goes around the corner, it does the opposite. Will that be a good thing or a bad thing?
Oh, where anti-roll, where it
Yeah.
goes into the turn?
Yeah.
That could be done. The simplest way to do it is to put your center of gravity below the roll center. That car will indeed, as you go around a corner, that car will roll inboard. Unfortunately, we can't get our CGs down that low. The race car manufacturers try very hard to do that. They get as low as they can, but engines have to be high, people have to be somewhat high. Yeah. But you could do it with what's called an active suspension. Active means you don't have springs, you have hydraulic actuators.
Yeah,
here.
that's
Yeah.
what I was.
Yeah, and that when they were exploring active suspensions a lot in the 80s and 90s, they could do that. They could make cars roll in. They were pretty awesome. But it takes a lot of. It's very expensive and heavy to do active suspension, so generally it's not that. Okay. We talked about precession, recession. Here's a great example why you might want to have recession. So an off-roader hitting a big rock. If the wheel goes just straight up and down, that's okay, but the wheel can get out of the way of this rock better if it could go that way as it goes up. So that's recession. Now these two terms, they're definitely related to how the wheels handle bumps, but they are also related to these other terms called anti-dive and anti-squat. And sometimes they line up in ways that helps you, and sometimes they don't. So let's see. I think I need a picture. Okay, here's a rear wheel, and that. Here's the car. Inside the rear wheel, there's a suspension, and I'm going to put the center of gravity of the car right here. And let's see, I need to make sure I get this right. That's your. I'm going to not do it numerically. The mechanics get a little complicated. Let's see. If you know that when this car accelerates, so CG here, it's got an MA to the back when it accelerates, force on the tire, that's going to cause the rear suspension to compress and the front to lift up. That's kind of the default condition. But if you're clever about how you do the rear suspension, you can minimize the amount that it compresses. And it's really just taking the same physics of jacking and roll centers and applying it in this view. So we know that this rear suspension will have a pivot in this rear view, so that the tire is moving about some pivot here, depending on the suspension design. That pivot could be way out here, could be very close, but let me put it as you see it here. That's just like having a link like that. And the very same analysis that we did before, where that force has to be directed along that direction, starts to show up. If this force is directed in that direction, it has a vertical component. And that vertical component keeps the rear suspension from compressing. So that's called anti-squat. The way you calculate it gets kind of complicated depending on the kind of rear suspension you have, but there are formulas, as long as you know the suspension you have, and if you did the free body diagram carefully, you'd get the right answer. In some cases, you draw these lines from the center of the wheel, and in some cases, you draw them from the contact patch. That depends on whether you have a drive shaft coming into the wheel or whether it's a solid rear axle. But I don't think we need to worry about it at this point. The main idea is that this kind of an upward pivot is good to prevent squat, and it's good for recession, because at this point, this wheel path is going in that direction. So if this hits a bump, you're getting the wheel to go in the way you want to get out of the way of the bump. Now, there's another thing you can do with the front suspension called anti-dive. So it's just the reverse of what I'm looking here. This is an acceleration force moving the car forward. Now let me switch this to braking. In braking, you have a big force there. Your MA force, for those that missed last time, the reason I'm doing MA like this, you know that sum of the forces equals MA. Therefore, if I subtract MA from both sides, sum of forces minus MA equals 0. Now, this looks just like a statics problem. So you just draw your forces, you decide which direction is A. Well, if I'm decelerating, the acceleration is that way. Therefore, minus MA is right here, the other way. You just draw that on the free body diagram like another force. You call it the MA force. And now you can analyze this vehicle just like a statics problem. You don't have to think dynamically. It's easier to visualize. So here's the force on the front wheel. We know that normally this car will dive. And that's not, drivers don't like that because it feels disconcerting to kind of go over the front wheels like that. So the very same kind of analysis I did in the back applies. If you make this wheel pivot about some point, let's say here, now this can be a real pivot or a virtual pivot, then that's like having a link here. This force turns into that force. That force has a vertical component. That vertical component keeps the suspension from compressing. So that's very handy for braking, but look at the wheel path. If this point is here, my wheel path is that direction. Now if you come along and hit a bump, you lock up the suspension. So anti-dive is nice for braking, but when it hits bumps, the suspension is not going in the right direction. It's going really quite opposite. Like, put it this way, this rock will put a force on this tire. Very small bumps will put a force on the tire like that. Big, little bit bigger bumps will be putting forces like that. Really big bumps for your off-road stuff, that might be like that. As soon as this force is perpendicular to the path of the tire, you got no suspension travel. It locks totally. So this is why for, I'm trying to find a picture, but trophy trucks, like, they have the opposite of this. They, actually, no, let me not jump ahead that far. First, let's say, so here's this kind of link. How do I get from the double arm stuff that we looked at to that link? And a picture of that. So remember this picture. So in this case, if the inner points, we can ignore the caster, the inner points are parallel. So this wheel just goes straight up and down. So it has an instant center all the way to infinity. And that, in this picture, would be like that arm being like that. So that's within that, all the way to infinity. So this wheel just goes straight up and down. Okay, so how do you how do you get from the double arm geometry to where that point is? Oh, that was the best picture. What's that philosophy? That picture, that's a pretty good one. So this one happens to be parallel. Here the contact patch is moving that way. The incidence center in the side view of this wheel is now down in infinity there. So it's wherever these red lines intersect. You take the inboard points where the suspension mounts to the car, draw lines to them, wherever they intersect, in this case infinity, that determines this location. So it could be there. So for most street cars, it's maybe around here, kind of in this neighborhood. For off-road cars, it's going to be probably down there. So that will be much nicer for hitting bumps, but it means that when you put on the brakes, you're going to get extra dive.
I don't know how accurate this is, but just from the videos that I've seen of the competitions, it's, if a car does roll, it rolls over the front, going like downhill. It's like I've seen several. I haven't seen a car roll over on the side at all.
Yeah.
On turns, but I've seen a lot of cars just go over the front.
Yeah.
So as you design the suspension, I don't know the implications of that, but.
Yeah. So there's those are kind of they're related, but they're kind of separate issues. So this is a good point, though. So what he's bringing up is roll over when you're upside down. This kind of braking behavior, this is just a few degrees of angle of the car, like 5 degrees. When you roll over, that's when you've hit such a big bump here, for example, that this MA force combined with a short wheelbase. So let's see, how you roll over when, yeah, this is easy. Here's an MG, there's an MA. When those two forces combine to a vector, if that vector points, this is quite a drawing, is there any luck with it? If that vector points in front of the contact patch, that car is going to roll over. How many people can see that? Very good, yeah. So, so the phenomena of rolling over the front is a function of how much are you decelerating and where is the CG. If the CG is far forward and high, that's going to tend to roll over the front very easily. If you could put that CG down here, then the mg force here combined with the MA force means you would need a gigantic MA force to get that car to roll over. So that's an argument for trying to keep your CG low, and effectively it means you want a long wheelbase.
So, so when you dive, braking, does the dive help resist a rollover because it lowers your center of gravity, or does it?
Good question.
Does it just feel like you're going to roll?
It feels uncomfortable to the driver, but the actual height of the CG does not change typically.
Okay. It's
So,
just because you're both
yeah.
more than.
Yeah. It's just a pitch of the vehicle, but it's not directly related to where that vector is pointing.
Okay. But like safety-wise, it really doesn't impact your chance of actually rolling the car that much.
I don't think it does. Yeah. Yeah, great distinction. Yeah. Okay. Let's see. Okay, so we've talked about roll. Okay, precession, recession. So there are a few things to know. So there's anti-dive. That means when you put on the brakes, how much does the front spring compress? And there's a formula for that. And there's anti-lift as well. So that is, so when you put on the brakes, even if this off-road car needs to have a front wheel that has pro dive, you can still get the rear from coming up. And actually, many drivers find that's more uncomfortable. The front going down is not as bad as the rear coming up when you brake, like just human perception. So you can get what's called a lot of anti-lift on the rear. And that you can achieve because it's exactly the same as anti-squat. If you get anti-squat, you also get anti-lift. And then there's anti-squat, and there's different formulas for the kind of suspension you have. This is an IRS, independent rear suspension, and if it's a stall axle, it's done a little bit different way. I don't think we need to go into that now. That's more of the suspension team needs to know that, but not that good. Sprung versus unsprung map. Before we go there, questions on pre-session, recession, pitch. Okay, let me get a sense, is this the right speed or too slow or too fast? Too slow? Right speed? Too fast? I'll stick with springs. Yeah, this will be better. Okay, so we know that the springs are between the wheel and the frame, and there is an important thing called the motion ratio, which is the amount of sorry, there's a way to make this go away. So we want to have, I think it's time to kill that one. Okay, we know we have springs between our car and the suspension. And I'm going to do a very simple suspension, just so that things are easier to explain. That's a double A-arm, this is a swing axle. We have our static weight reacted. So if it's a 300-pound car, then and it was 50-50 weight distribution, then that'd be 75 pounds on that wheel. The wheel itself and the axle, let's say that weighs 10 pounds. That means there's 65 pounds that the spring has to take. So how do we get from that 65 pounds to the actual compression of the spring? And so this is a little derivation here. Okay, the first thing we define is called the motion ratio. And this means if I take the wheel and I move it up 1 inch, how much does the spring actually compress? And it will be almost always less than that 1 inch. See, the way you figure it out, like in a really simple way, if this spring were perfectly vertical, then you would simply take this distance, call it A, and this distance, B, and my motion ratio would just be B over A, simple lever. Now when you get into more complex suspensions, Those usually have a pivot there and another arm here. If you have a pivot there, then it's not that whole distance A, it's only that distance.
So you have to have a continuous like, piece of metal.
Well, the first one I showed was called a swing axle. That suspension where the wheel just pivots like that, and that's a bad suspension, but it's good for initial explanations. This is a double A arm here, and this is the lower ball joint, that's the upper ball joint. Did that answer your question?
Kind of, yeah.
Try it again. So motion ratio would simply be B over A. Now, if you incline the spring, you're going to lose some of that motion ratio, and I'm going to let the slides do the talking now. Better. Let's see, this has that. Oh, that I switched my A's and B's. Here we go. If you incline the spring by an angle alpha, then you need to account for that, that as a cosine. And you see these squares here. That I need to derive in another way. Let me jump around, but let me go back to here. So just in terms of motion ratio, here we have a distance, yeah, that's, some people do AB and some people flip it. So, and some people define the angle here, and others define it between that and the vertical. So that just is a sine versus a cosine. You can get this geometrically with these kind of formulas, or you can do it with computer software that'll move you through the motion. Now there's, let's see, there's another important thing related to the motion ratio, which is how does the spring rate, AS, relate to what we call the wheel rate, AW? And it's a little bit surprising how this works. I'm going to go back to my simple swing arm because for easy explanation. Let's see. In terms, first let's look in terms of force. So this is B, and this is A. Okay, we know that if this is the reactant force R, and I put if I put say I put 10 pounds in at the wheel, and that's a pivot, then we know this reaction force R will be bigger than that 10 by the ratio A over B. That's 10. We also know if we move this wheel 1 inch, that the deflection at this point, delta, will be less than that 1 inch by the ratio B over A. Deflection is B over A times 1 inch. When you look at the spring rate, you know that that is a load, a change in load, over a change in deflection. So, if I have a change in load that was defined by this ratio, did we do this wrong? Yeah, that was multiplied, yeah, okay, that's gonna work out. The load was defined by an A over B. The deflection was defined by a B over A. So the net spring rate is going to be an A squared over a B squared, or an A over B squared. I'm sure I explained that very well. Let's see if you guys get the step of the logic. So we know that change in load, change in deflection, force here and there'll be some deflection here, but that doesn't really, I'm just trying to leave that out of it. The important thing is that you get there we go. This is another variation very similar. That the K wheel, the goal was to relate what's the relationship of this K wheel to the K spring, and the relationship goes by the square of the motion ratio. One of the squares comes from the force, the other of the squares comes from the deflection. So the relationship is K wheel equals motion ratio squared times K spring. I threw this lecture together in like 2 hours this morning. I didn't get all my pennies straight, sorry.
Do you remember by K of the wheel, do you mean the deflection of like the tire? Or just-
Well, the effective spring rate at the wheel. So, meaning, let's see, how would you say this? Another way to say, if you were jumping up and down on the car right here, and you jump down with 10 pounds, that would put, you know that would cause 10 more pounds on the wheel. So how much would the suspension deflect? Technically, you're jumping down right over the. So you put a force there, you got a little ledge, so that your force would directly react to the wheel. You know that the suspension is going to compress. How much will it compress? That's determined by that.
How would you know which spring to buy?
Yeah, so very good. So usually we have targets for our K wheel. This is kind of, I didn't prepare this at all, but I'm going to give it a shot because it's a good point to bring it up. Let's see. So this has to do with what's called the ride frequency. Okay, so when you model a vehicle, this is just one corner of the vehicle. That's the sprung mass. Or we can pretend our car only has one wheel. It's a unicycle. And it has a spring. Then it has a tire and a wheel and a suspension. That's the unsprung mass. The tire has its own spring relative to the ground. This is K wheel, this is K tire, and then the ground is here. And the ground can move up and down. So that's kind of this would be like this. The one-dimensional model of the suspension. Sprung mass, we want to maintain relatively stable. This thing is going like that. And we want to know, well, KT you can't do a lot about except for air pressure. You want this to be as low as possible because if you're doing this and this is heavy, then it's going to get thrown off the ground and then it's going to land back on the ground with a big impact. So ideally this is massless, has no mass whatsoever. And then the ideal for this is for it to just gently go along, not have a lot of bumps. So since you have a mass and a spring, you can define an omega. And that's the ride frequency, square root of K over M. So M, and that would be K wheel. And just by trial and error, people have learned what kind of ride frequencies work well for most cars. And I think 1 hertz is a pretty common, in the neighborhood of 1 hertz is where they are, most ride frequencies. And so this is a non-dimensional way of comparing cars. A 300-pound car and a 3,000-pound car will usually have pretty similar ride frequencies when they're tuned so that the drivers like them. It's a way, just a way of non-dimensionalizing.
So it doesn't depend on the kind of road that you're.
It does. No, you're absolutely right. A race car on a very smooth track might have a 3 hertz frequency because they don't need to have much suspension movement. And an off-road car probably is under 1 hertz, but I don't know. I haven't seen any data. Yeah, great question. So let's see. So your question was on how do you pick the spring rate? First, you determine how much sprung mass is on the corner. So that's your load distribution, take away the unsprung mass. Then try to get some data on what omega works well for this kind of a vehicle. And so hopefully someone in Baja Forums has published their ride frequencies. I bet they have. Then, so if you know that, and you know that, you can solve for your K wheel. Once you know your K wheel, we can now get our K spring by knowing that and the motion ratio we get from the geometry. So that's the last thing you get. That's the path. So write down that path. What's that? So one is decide on omega. 2, calculate unsprung corner weight. That's that big M.
Oh, it's sprung.
Yeah, unsprung. Oh, sprung. Sprung. Yeah. Thank you. Yeah, sprung